Hey, Carl! Our programs here are in too many languages! Make one that fits all of our use cases, now! This is the plot of an XKCD comic. Do I look like I care? No! Stop talking back to me and follow orders! So, introducing gurgling. It exists. Oh, so you thought that the problem, which was that we had too many languages, could be solved with another language? Nobody's gonna switch to it! You just made the problem worse, idiot! Why am I still here? There's a door right there. I should just walk out of it. Hey guys. So, over a span of about a couple days that were, at the time of writing, about last weekend, but probably when this finally gets released, several weeks to a month ago, I made a small programming language called Flug, and this video is about how it works. Flug is also a rather simple and straightforward programming language, so much of this video will also apply to how programming languages as a whole tend to work. So, let's start with what Flug code actually looks like. This program outputs the first 7 factorials, and it pretty much shows all the features that Flug has. It's got if statements, mutable and immutable variables, loops, first-class functions, and a built-in output number function. Flug is an interpreted programming language, meaning that Flug itself is a program that you feed code files into, and that program reads the code and does whatever the code tells it to. This is different from a compiled language, where you feed code into a program, and that program spits out a new file that can be run on its own or with some type of runtime. Like most interpreted programming languages that exist, that aren't esoteric ones, Flug is made up of 3 components: the lexer, the parser, and the interpreter. And in Flug's case, these are all written in Kotlin. Let's start with the lexer. A code file, on its own, is just a sequence of symbols, which is really just a sequence of numbers. The lexer's job is to look at these symbols and turn them into actual tokens that the program can better use. So let's take this example and bring in our good friend Creaturey to identify where all the tokens are.
So let looks like a token, and I'm pretty sure the equal sign is too, and I think the semicolon's a token as well.
Yeah, that's right. Now, what about the X and the 4?
That's easy. There's an X token, and there's a 4 token.
Creaturey, that's completely wrong!
What? Huh? But there's an X and a 4, what are they?
Well, they are still tokens, but there's no special X token and there's no special 4 token, because if we were to do that, we would never finish writing the language. Instead, X is an identifier token, with X being its value, and likewise 4 is a number token with 4 as its value.
So there's a token for X and a token for 4, so I was kinda right.
Yeah, whatever helps you sleep at night. So now that the program's all tokenized, can we run the program now? Well, in the wise words of Zazu from Lion King, not yet. While it's much easier to deal with tokens than plain strings, the program still hasn't been structured in an interpretable way. It's still flat, while code behavior is usually supposed to branch. Not to mention scope is a thing. So, how do we do that? So let's take a look at this expression. You can look at this if-else statement as, if something, then something, else something. And what are those somethings? More expressions! And those expressions have their own parameters too. The equals equals, for example, is something equals something, and it keeps going recursively. Some languages, by the way, differentiate between expressions and statements, but for simplicity, Flug doesn't. So while, for example, an if statement in some other programming languages might not return anything, in Flug the if statement returns whatever is in the true or false state, depending on which one actually gets run. Eventually, we reach a point where there are no more expressions to plug in. The number expression 4 is just 4. And as a whole, the program can be structured as a tree, an abstract syntax tree, or AST. The AST is what the interpreter actually looks at, and it's generated by the parser from the tokens. Sometimes the parser is actually generated automatically, but with Flug I decided to write it myself. Flug has a basic top-down parser. In this structure, parsing is called for each operation in increasing order of precedence. For example, since we want to follow order of operations for arithmetic, we want multiplication to happen before addition. As a result, we want multiplication to bind tighter than addition, and so we want to run the parser for addition before multiplication. Also, we parse from left to right, so that the expression 8 minus 3 minus 2 resolves to 3, and not 7. Wait. Why are we parsing backwards? We want to run multiplication first, but we're parsing addition first? Yeah, because we want multiplication to be deeper in the tree than addition. So addition will add together the two results of the multiplication. The parser is also in charge of making sure that the code is correctly formatted as well. So in this example, the parser sees let and knows it's doing a variable declaration, resolves the x identifier, and then it makes sure to check that there is in fact an equal sign there before parsing whatever comes after that. Otherwise, the code isn't formatted right and it throws an error. So now there's a parser, and we get an AST. Now we just need to interpret the AST.
Actually, this is part 4, because the AST section was its own section with its own title card, you bozo! I don't care about half sections, it was a whole section!
No, actually it's part 3. I, just now retroactively decided to start indexing at 0. So now we have an AST, and we want to interpret what it does. Starting off, interpreting a number containing 3 will just return the value 3. For interpreting an arithmetic expression, we just perform the operation, like addition, onto whatever we interpret on the left and right side. Now for variable declaration, things start to get a little bit more complicated. Where do we store the variables? Shouldn't this be obvious? We just keep a mapping from the name to the value. Duh. Well, it can't just be any mapping. Why? Because of scope. Take this expression. The C inside of the if block only exists inside of the if block, and if we try to use the C outside of the if block, we get an error. So the interpret function takes in not just the AST node to interpret, but the current environment as well. We start with an empty environment, and when calling interpret recursively, we usually just pass the same environment that we received. A new block, though, creates a new child environment based on the old one, and the let AST node adds variables to the environment. One more interesting part of the interpreter concerns function declarations. Flug functions are first-class functions, and they're treated the same as anything else you can assign a variable name to. And since the function body is an expression, nothing is stopping you from declaring a function inside of your function. And you can also assign variables inside of your functions. So you can create nested functions like this one.
Hold on a second. The inner function here refers to x, but if we were to do something like let q equal f, and then call q of 1, that will call the inner function, but q isn't in the scope with x anymore. Even though, if I were to just look at this, it should just use the same x as the original call to f. So, what's happening here?
Closures! When a function is declared, the function's environment that it started in is kept alongside it. That way, if a function is inside of another function and that function has variables, the inner function can use them even if it's called from outside of that. Which means that Flug can do things like, for example, having immutable pairs, which is kinda cool. And also, that means that Flug can compute anything that you can compute in lambda calculus, which means that Flug is Turing complete. Additionally, it needs garbage collection now, but that's handled by Kotlin, so I don't need to do it myself. But if I were to write Flug in C++, I would have to do garbage collection by myself. But anyway, that's how Flug works. Yes, it's a pretty straightforward language, but it demonstrates how straightforward programming languages tend to work, which is why it exists. Anyway, Flug is available on GitHub if you want to try it out. The interpreter probably has bugs or issues that I haven't seen, so if you spot one, please submit a pull request. A special thanks to Tyler Zanke, Ai Hashibami, and all the other channel supporters, and I'll see you next time.